Hello everybody, and welcome to another session of the PCE3 seminar series, which is organized by NASA. And this is focused on highlighting work of some early career researchers in prebiotic chemistry and early Earth environments. And today we're lucky to be hearing from two PhD students, Lukas Rossmanith and Skyla White, who are both working at the University of Cambridge. And we will have some time for discussion once both speakers have finished their presentations. So if you have any questions that pop up during the discussion or during the presentations, please make a note and we'll be able to get to those at the end of the talks. Now, before we hear from Lukas and Skyla, we also have a topical introduction that's going to be given by Professor Paul Rimmer, who's also working at the University of Cambridge. And Professor Rimmer is an expert in how impacts in volcanic systems affect early Earth and planetary environments, and how these factors play a role in prebiotic chemistry. And so, yeah, thank you to all of us. Thank you to all of you for joining. And go ahead, Paul.
Great. Thank you. Thank you, James. Thanks to Zoe and James and the other organizers for just giving us an opportunity to share some of the work that we're doing. And thanks to all of you for being here. I'm just here to give a very brief overview. The lab here we call the Planetary Astrochemistry Lab. And you'll get a better idea as to why from Skyla and Lukas's talks. So just to give a very broad overview, this is a picture of the other members of the lab, the other students and postdocs, whose work you'll hear a little bit about in Skyla and Lukas's talks, but who have their own projects related to this sort of approach towards trying to understand where life might have originated and how. So the sort of brief overview is there's this kind of picture of starting out with a very low degree of aliveness, some sort of plausible environment, atmosphere, surfaces. These can lead to small molecules, which can come together somehow to make life's building blocks. These building blocks can polymerize. They can get incorporated into this kind of protocell. They can hold and copy information, and maybe these protocells can make copies of themselves at some point in time. And there's this sort of idea that if you're in the right kind of environment with the right kind of mechanisms going on, there could be one or potentially very, very many pathways toward moving toward this greater complexity, to this greater degree of aliveness. And so, but there's the question of what path. And so different people take different paths, starting from different places, oftentimes informed by life as we know it and what life seems to need, especially from a bit of a reductionist perspective. Life needs a container. So, and for life as we know it, this is provided by these phospholipid membranes. Life needs some kind of informational polymer, some way of storing and copying information with a very, very high degree of accuracy, but not perfect accuracy, so that Darwinian evolution becomes possible. And for life as we know it, this is done through DNA and potentially could be done through RNA. Life also needs some way to control its chemistry. The chemical environment of life is very far from equilibrium. This is largely done by proteins and other enzymes, and the proteins are made of amino acids. And then there's some sort of metabolism. There's some sort of way of taking complex molecules and breaking them into energy that can be stored in other forms of molecules, or that can take energy from those molecules or from the environment and can use that energy to build up these building blocks of life. And different approaches may start with just one of these kinds of molecules. It turns out life the systems of life mix up all of these different categories. And so one promising approach seems to be to take multiple of these categories, if possible, and have them all kind of working together right from the beginning. But a big part of this is that we just don't know where to start, and chemical parameter space is very, very large. There's also the question of where life might have originated, and underwater hydrothermal vents is one possible environment that's been proposed. Surface hydrothermal vents is one that I'm particularly interested in. Alkaline lakes. By the way, these citations are certainly not comprehensive, so please don't take offense if I didn't mention your particular paper here. This is just to give a sort of overview of the many environments. Underground, Tommy Gold, Barbara Sherwood Lawler, and various other people have looked at what sort of prebiotic chemistry can happen through radiolysis and serpentinization underground. Basaltic glass, there's been some really interesting work recently from Benner's group. Some really amazing long polymers can form on surfaces of this basaltic glass. Craig Walton has been looking into cosmic dust, which can deliver a lot of interesting chemistry, which can be concentrated in certain early environments. Giant impacts have become have long been a popular scenario and kind of returned to, especially the very large impacts have kind of returned to a sort of limelight. But all of these, any of these, one of the big things that our approach has is looking at the connections between chemistry and geochemistry. The chemical parameter space, as I said, is effectively infinite. The possible environments are exceedingly diverse. But if you can't make or test predictions, then you're not really doing science. And so one of the approaches that we have is under the assumption that life isn't too hard to start. That if we kind of wander the parameter space, we can find some interesting places where we can discover some new chemistry and maybe make some real headway to solving this. We look to the combination of environment and chemistry. So you might start with a particular chemical pathway. You would look at the environments that would give you your starting conditions and the sort of mechanisms that you could work with this. Then you would, it's an interdisciplinary or multidisciplinary approach. So you would work with geoscientists, geologists, planetary scientists to figure out what else comes with those environments, chemically and physically. Incorporate those to see if those are still consistent with your prebiotic chemistry, and iterate. Largely with the purpose of trying to rule things out so that we can get an idea of what can and can't happen. But you're ruling out not a specific chemical pathway or a specific environment, but the combinations of those pathways and environments. And in this, we focus not so much on the initial conditions, but we focus on specific mechanisms and whether those mechanisms can happen fast enough and in an orchestrated way to really lead to the complexity that you see in the lab. Can this happen in a natural environment? In some cases, incorporating aspects of the natural environment can help things work better or worse, and oftentimes better or worse depends on a combination of those initial conditions and just how fast the chemistry happens to occur. And to really know what that is and be able to apply that with models or simulations to a wide variety of environments, you need to measure rate constants. And so we're really interested in aqueous chemical kinetics, and you'll see a nice talk by Skyla White of how this has been applied within our own solar system, and a nice talk by Lukas Rossmanith for how this can be applied to exoplanetary systems to talk about what kinds of prebiotic scenarios might be able to play out and what constraints we can put on some of those scenarios, focusing, of course, on what you know best about any exoplanet system, which is the light of the star. So that, I hope, gives the context, and I hope you enjoy what Skyla and Lukas have to say.
Great. Thanks, Paul.
Sure thing.
For the great introduction. And now we'll move on to our second speaker, who is Skyla White. And she received her bachelor's from the University of Warwick and her master's from the University of St. Andrews. And now she's pursuing her PhD at the University of Cambridge, working with Paul Rimmer in the Planetary Astrochemistry Group. And Skyla's research is focused on the kinetics of ultraviolet-driven prebiotic reaction networks and developing models of life's origin. So thank you for joining us, Skyla, and we're excited to hear from you.
Oh, hi. Yeah. Thanks, Paul, for the great introduction to what we do. And thank you also to the seminar organizers for inviting us to come and share some of the things that we've been working on. In particular, I'm going to talk to you about a project I've been working on, which involves exploring what is known as the carboxysulfitic scenario. If you've been attending these seminars for a while, you might actually remember a talk from a while back, quite a while back now, by Ziwei Liu, who originally proposed this chemistry back in 2021. So if you attended that, you might be able to draw some parallels here. So throughout my PhD, most of my work has been focusing on measuring the kinetic parameters that are associated with different prebiotic reaction networks, with the aim of being able to place constraints on what geochemical environments will best facilitate the production of key precursors to life. Essentially, I've been trying to make strides towards bridging the gap between the chemistry we perform in the lab and the environments in which this chemistry would have had to occur. And so to do this, as Paul mentioned, we really need to rely on insights from kinetics. When measuring kinetic parameters, we focus on...
Skyla.
Yes.
But, I think on my screen, okay, now it looks good. For some reason, we were getting that weird. I think it looks okay now. Sorry. Go ahead.
Okay, no worries. Yeah, let me know if it happens again. When measuring kinetic parameters, we are focusing on deriving rate laws. Rate laws are there to describe the relationship between the rate of a chemical reaction and the concentrations or the activities of the reactants within the system. And then from these rate laws, we can determine rate constants, which represent the intrinsic speed at which a particular chemical reaction occurs under specific environmental conditions. And so that's what this equation here is representing, the kind of way that we can relate rates to reactants and use rate constants. So these conditions can be varied to assess how the behavior of the chemistry will change in response to different environmental factors. Some of the factors being measured in our group in particular include things like temperature, the presence of spectator molecules, pH, and solar radiance. However, all of these factors and more will need to be investigated in order for us to actually place useful constraints on the geochemical environment most conducive to whatever chemistry we're exploring. So before I continue, it's quite important to ask the questions of what do we actually mean by a prebiotic reaction network, and why are kinetics so important for understanding the emergence of life? Well, prebiotic reaction networks refer to a series of chemical reactions that likely occurred on the early Earth, so prior to any kind of onset of life. And these networks are typically involving quite simple organic molecules, and they describe the production of more complex compounds, so eventually trying to get towards things like nucleotides and simple sugars. And understanding these networks is crucial because they can offer insights into the pathways that might have led to the formation of the really complex things that life uses and that life is made up of. However, it's quite important to understand that just the mere existence of these pathways isn't enough. We need to be able to consider how these reaction pathways persisted in relatively diverse and fluctuating conditions on, say, early Earth or early Mars. And this is where the kinetics actually becomes quite essential. The kinetics helps us to determine the plausibility of these prebiotic scenarios by focusing on the rates at which these chemical reactions occur within a given environment. So in order to determine whether a reaction will proceed for a reasonable length of time, the timescale required for a reaction to happen within a specific geochemical environment must be faster than any of the processes that would end up leading to the removal of the reactants. A simpler way of putting it might be that the chemistry needs to be robust enough to continue despite any kind of external influences or perturbations. This robustness is quite important to us because it's a trait that a lot of biological processes share, and usually we see this as being due to enzymes. This means that we still have the question of how could these networks have persisted prior to any kind of enzymatic control. In the absence of these enzymes or any kind of refined laboratory procedures performed by us chemists, we suggest that the geochemical environment itself might have played quite a large role in helping to regulate these chemical networks. And this control could come about in many different ways, for example, adding buffering capacity or creating redox gradients or helping to kind of foster autocatalytic characteristics within the network. And so to determine these controlling environments, we measure rate constants. The diagram that you can see here is an example of this, where we essentially have relatively productive chemistry in the laboratory, where we're going from this S1 scheme to S2, and we're getting a relatively high yield. If we were to then move into a kinetically unfavorable environment, such as the one shown in the middle, what you might end up having is side reactions that lead to a lower yield of the desired product, and it might lead to the lack of persistence within the network. Whereas if we were able to go to a kinetically favorable environment, such as the one seen on the far right, then we might be able to kind of force the chemistry in a direction that we think it would be the most desirable to go in terms of the products that we want. A slight caveat to this, which I'll return to a little bit later, is that while individual prebiotic reaction networks are useful for mapping out these potential pathways, it's really important to understand that there are problems that can arise from studying these networks in isolation. And this is because integrating multiple networks could actually alter the behavior of the chemistry, and that could change our view on how robust certain reactions actually are in a given environment. And this is what Paul was kind of getting at when he was talking about how the development of models that utilize these kinetic parameters would really help us to try and navigate this quite complex web of reactions and enable us to see the interplay between multiple networks and such. So as part of my research, I've been putting some of these ideas into action by studying the kinetics of a very specific reaction network. So this is the carboxysulfitic reaction network, and was originally proposed in a paper by Ziwei Liu and co-authors in 2021. And in this work, they propose a way of converting carbon in the form of carbon dioxide into organic molecules. And this is a process that has traditionally required quite high pressures or high temperatures, and ultimately has resulted in quite low yields of useful products. So the way in which they do this is by utilizing UV radiation to produce solvated electrons from sulfite that can end up reducing carbon dioxide. This initial reduction of carbon then triggers a network of reactions that generate important organics, such as the ones I've just outlined here: formate, glycolate, citrate, malate, succinate, and tartrate. And one aspect of this chemistry that really makes it so promising is the, I guess, simplicity of the chemistry and the widespread availability of its starting materials on rocky planets such as Earth or Mars. And so this work suggests that such reactions could have naturally occurred on the early Earth, potentially facilitating the development of, say, a central carbon metabolism before you end up having the advent of biological carbon fixation. And so all of these ideas make this a really intriguing network to investigate the kinetics of. So just talking about the network in a little bit more detail, as you can see, the reaction starts on the top left, which is what I've blown up here with the production of solvated electrons. As a brief aside, these electrons are formed when a molecule or ion is able to absorb a photon from the UV light. And when that happens, an electron within the species can be completely detached and solvated. And these electrons end up being highly reactive and thus can go on to partake in lots and lots of different reactions. In our case, as you can see here with this SO3, we can combine this electron with carbon dioxide, creating a radical species, which is number 12. And then you can have sequential reduction of this radical, leading to the production of single carbon compounds. So these are things such as 2, the green one there, which is formates, or you can have dimerization of the radical, leading to multi-carbon compounds. So these are things such as that orange one down there, 10-oxalate. And so in the work presented here, we actually choose to focus on the very first step of this network. So we are measuring the rate constant associated with the production of formates in particular. So in order to place constraints on the environment in which this chemistry is the most productive, we measure this rate constant under different conditions. And so we had to go about trying to choose which condition might be the most useful to vary in this context. One relevant thing might be to assess the impact of stellar variability, given the network's reliance on solvated electrons, which require UV. And so Lukas, who'll be talking to you after me, will discuss the impact of stellar variability on single prebiotic reactions. So you'll hear a bit more about that. And then another interesting factor to investigate might be the presence of things like spectator molecules. So these are other molecules that might end up interfering with the chemistry by either blocking UV light or leading to side reactions that cause the production of undesirable products. And this, as well as the impact of temperature, is something being investigated for alternate reaction networks in our lab by Dr. Simon. And then finally, the parameter that I find the most interesting and have been testing is the pH level of the aqueous solution. pH is something that varies quite a lot between different proposed origin of life environments. And so the idea was that determining rate constants as a function of pH should help to narrow down the environments most conducive to this chemistry, or where we might state that this chemistry is the most productive. As a bit of an example, this table here shows just a few examples of relevant environments and their different pH ranges. So hopefully you can see here that the pH varies quite a lot, ranging from pretty acidic in these surface hydrothermal vents to actually quite alkaline in certain types of marine hydrothermal vents. So there's a big discrepancy between the pHs of these environments. So now we've chosen a reaction network and we have decided on an environmental factor to vary. How can we actually try and constrain this chemistry to a specific environment and the environment to a specific chemistry? Well, we are going to start by deriving a rate law for the production of formate based on the different mechanisms by which we think it's produced. We can then determine the rate of production of formate as a function of pH. And then using these rates and the previously derived rate law, we can calculate rate constants as a function of pH. If we then compare the established rate constants at each pH, we can determine under which pH conditions resulted in the highest rate of formate production. So that's what we did, and I'm going to talk to you a little bit more about how we did that. We're going to start by setting up our reaction. This involves being able to simulate ultraviolet radiation required for the production of the solvated electrons. And so for this, we use a broadband laser-driven light source, which is shown here. This source has quite a wide wavelength range, so it's transmitting light between 200 to 800 nanometers. And we
Skyla?
use the lenses here. Yes?
Oh, sorry. I think now it looks okay, but for a while, I think your slides are kind of having that problem we were seeing before. But for now, it looks okay. But on some of the slides, it's been happening. I'm wondering if you'd want to try to close your. Is that what we did before? You closed it and then reopened it.
Hello.
Oh, okay. Sorry. Did you?
Hello. I think we got kicked out for a second there. Can you hear me all right?
Yes, we can
Yeah,
hear you.
the bad cock on this day of all days seems to be having horrible internet problems. Apologies.
But yeah, now your slide, it's showing up nicely, I think. But we were
Okay.
so yeah, sorry to interrupt, but
No worries. Please just do interrupt again if it decides to disappear.
yeah, thank you again.
Okay, so yes, hopefully now you can all see the picture that's up here. So we've got our light source and we are using these lenses at point number 2 to focus this source on a quartz cuvette, which holds our aqueous solution of sodium sulfite and sodium bicarbonate, as well as a mixture of buffers depending on the pH we are investigating. So this is a spectrum of our light source here. As you can see, it's quite intense. And so this means that in order to draw any meaningful insights, we need to place our results in the context of the sun on the early Earth. And to do this, we can compare the spectral irradiance of the laser-driven light source to the spectral irradiance from the young sun at either the distance from the sun to Mars or the distance from the sun to Earth. And from this comparison, we can determine scaling factors by matching this irradiance of the LDOS, which is our light source, to the irradiance from the predicted solar spectrum. And so that's what you can see with these blue lines here, where we've essentially taken our maximum intensity of our light source, and we've determined scaling factors to match that to either the young sun at Earth or the young sun at Mars. So now that we have our setup, we can actually derive our rate law, an empirical rate law based on the concentrations of the reagents used in the experiments is what we can see first in this first box. And then in order to determine the order with respect to each reactant, we varied the concentrations of each reagent individually whilst holding the other one in excess. And this allows us to rewrite our equations as follows, where we can make it so that it's just a function of one of the reactants involved. And then by performing linear regression analysis, we can determine the order of reaction with respect to bicarbonate, which ends up being around 0.71, as you can see on this graph. And then we can do the same thing for sulfite. So looking at the dependence of the rate on sulfite concentration, we actually see a negative correlation with increasing concentrations of the sulfite, actually leading to a decrease in the rate of reaction. And we suggest that this order here of around negative 0.6 could be due to some sort of self-shielding effects. Yeah, we've come up with a sort of an analytical model to describe that, which I won't have time to go into today. But yeah, so based on this, we can rewrite our rate law in the final form, which is that final box there. And that's what we're going to use going forward. We next determine the rate of production of formate as a function of pH. So we measure the rate using constant concentrations of sulfite and bicarbonate, and we measure the rate in intervals of 15 minutes, starting from 30 minutes and irradiating all the way up to about 2 hours. We then perform linear regression analysis at each pH, and using this, we can determine the fastest rate of reaction. And here, as you can see, we found the highest rate of formate production to be at pH 9, with the rate at pH 6 being around 50% lower, and then the rate at pH 12 being significantly lower than that. This is in line with what we actually might have expected, as at such a high pH, you would anticipate very low concentrations of both dissolved carbon dioxide or bicarbonate, as most of the carbon in the system should exist as carbonate, so CO3 2-, which is not a reactant in this chemistry. So we've essentially reduced the amount of reactant that we have. So as we now have rates and a rate law, we can start to determine the rate constants. One problem that we faced here is that as the rate constants are sensitive to reactant concentrations, we needed to be certain of the reactions involved in formate production in the first place. And due to uncertainties in the exact mechanism, we came up with 3 different rate constants based on the following schemes. So our empirical, mechanism 1, and mechanism 2. The empirical version is basically just derived using the reagents and their concentrations. Mechanism 1 is derived based on the original mechanism proposed by Liu et al. In 2021. And this mechanism is the one that describes the production of formate from the direct reduction of dissolved carbon dioxide to a radical species, and then that radical species recombining with a proton-giving formate. And although we think that this might be the most likely mechanism, we also have good reason to believe that the formate could be formed directly through the reduction of bicarbonate instead. And this is what we're seeing in mechanism 2. So for these rate laws, we use equilibrium concentrations of dissolved carbon dioxide, bicarbonate, and sulfite. And these are calculated based on the kind of initial concentrations of reagents and the pH of the solution. And we can do this using a simple model that accounts for the dissociation constants of different acids. Okay, so now that we've got those, we have different rate constants based on these different schemes. This table now shows those results accounting for this. Based on the empirical rate law, we found the highest rate constant to be at pH 9. The rate constant at pH 6 is lower, however, it does overlap with the lower end of the range that we determine at pH 9. And then we see a significantly lower rate constant at pH 12. So this is a very similar trend to what we saw in terms of the rates. And then for mechanism 1 and 2, we see an increase in the rate constant going from pH 6 to 9. However, mechanism 1 leads to the peak rate constant at pH 12, whereas mechanism 2 has the peak rate constant at pH 9. And so what this is really to highlight is that the mechanism has quite a significant impact on the reaction's productivity under different conditions. So studies that can elucidate the exact mechanisms for this would be quite important. As mentioned earlier, to kind of clean this up a bit, we can actually scale our rate constants to account for the amount of UV radiation that would have reached both the Archean Earth or early Mars. And here we can see these scaled rate constants. Yes.
So I hate to interrupt again, but I think, okay, it's very strange. Your slide looks okay now, but it's kind of, I guess maybe we should just continue. I'm sorry.
Okay.
Yeah.
No worries. Thank you. So yes, and what we can see here is that we've scaled them so slightly faster on the Archean Earth compared to early Mars because of the amount of UV that we end up getting. Okay, so following these results, we can begin to establish a set of criteria to try and define the environment that might be the most favorable for the production of formate via this network. And so the first thing that is quite vital to this chemistry is an aqueous system containing sulfites and dissolved carbon dioxide or bicarbonate. It is likely that both on the Archean Earth and early Mars, that sulfur dioxide and carbon dioxide could have been volcanically outgassed. And according to Henry's law, we would expect dissolution of these gases to be quite feasible if we assume equilibrium. The second thing that we can place a constraint on is the pH of the aqueous solution. We can do that now based on the work that we've done recently. And so whilst we acknowledge that all three of the pH values tested in this work did lead to some extent of formate production, the chemistry appears to be the most productive at a relatively alkaline pH. And we base this assumption on the highest rate of production of formate occurring at that pH of 9. Another key requirement for this chemistry are the solvated electrons, which are required to reduce the carbon species. And the production of these electrons requires UV radiation, meaning that the aqueous system would need to be relatively transparent to UV and free of alternate UV absorbers. So some work has actually already been done by Ranjan et al. In 2022, looking at different waters and their transparency to UV radiation. They found in this study that while prebiotic freshwater was largely transparent to UV radiation, if you have high salinity or ferrous-rich waters, you might end up having significant shielding of the UV light, and that will influence some of the productivity of these reactions. So whilst we can now start to lay out a list of all of the prerequisites of this chemistry, we can also outline some things this chemistry does not require. For example, it doesn't require any cyanide, it can happen at relatively low temperatures, and it doesn't need a closed system. And these are just to name a few. And this relatively short list of prerequisites and the lack of dependence on more intense conditions makes this chemistry quite a promising area for future research. Although we now have this criteria that outlines whereabouts we might want to look for this chemistry, it's quite tricky to find environments on Earth that might preserve signatures of carboxysulfidic chemistry. This is quite challenging because you have quite a vast alteration of Earth's rock record. One potential environment that we think might avoid this issue is that of Mars. So Jezero crater is of particular interest owing to it previously having hosted paleo lakes that are thought to be similar to some of the high carbon alkalinity lakes proposed to be prebiotically relevant by Kapling et al. And once again, if you've been listening to these seminars for a while, you might remember a talk covering some aspects of these lakes a few months back. So these lakes align quite well with our criteria for carboxysulfidic chemistry. And unlike on Earth, Mars presents quite a unique opportunity to study sort of less altered deposits that could have preserved organic compounds and therefore host potential signatures of different prebiotic chemical processes. This is a result of, the cold temperatures, the fact that you've had loss of surface water, etc. Therefore, one of the things that we would like to suggest based on what we found is that Mars sample return missions should focus on environments that have evidence of carbonate formation, as this would be indicative of quite a relatively alkaline pH. These environments should also be host to sulfites or sulfate minerals, which would imply high concentrations of sulfite might have been present in the past. We can note that NASA's Perseverance rover has in fact actually already discovered some of these sulfate-rich minerals, so magnesium sulfate minerals and anhydrous calcium sulfate minerals and such. And there's also been the discovery of iron-rich carbonates and magnesium-rich carbonates at Jezero crater too. So all of these findings imply that Jezero crater might have facilitated this chemistry in the past. And so should the Mars sample return missions be able to discover lake sediments that have been deposited within the photic zone with carbonate and sulfur-rich minerals, we might suggest that these minerals should be investigated further to search for inclusions of things like the formate, which we were making in this work, alongside some of the other products of carboxysulfitic chemistry, things like acetate and oxalates. Okay, so now finally, as I mentioned at the very start, the overarching purpose of measuring these rate constants is so that we can eventually feed them into an aqueous chemical kinetics model, making the work I've presented today essentially just the first step of a much, much bigger project. In the near future, we really hope, and it'd be good if we get some feedback today that a sufficient number of rate constants from a variety of different reaction networks will have been measured. And this will allow some aspects of prebiotic chemistry to be predicted using models. And once these models have then been benchmarked against experimental data, our next step will be to apply them to natural environments that better mimic the conditions that were actually thought to be present at the onset of life. This should enable us to make predictions regarding the time-dependent concentrations of prebiotic-relevant molecules under different conditions. So I'm hoping that you can see my diagram here. But this shows just a very basic outline.
It's a little bit, oh, there, okay.
Okay, so whenever I ask, it seems to work. So yeah, this is an example of a model that I've been developing here. It's a very basic outline, but essentially what we do is we take the atmosphere, we put it in equilibrium with an aqueous solution, and then we feed some inputs regarding the composition of this aqueous solution, along with information on reactions, rate laws, and rate constants into a processor, where we can then calculate the equilibrium concentrations of each species as a function of pH, and we can solve some equations for each species based on the rate laws that we have. This can then output species concentrations as a function of time and allow us to look at the way different reaction networks might interact on a wider level. So in order to truly realize the potential of this model, I'm building a database for the kinetics associated with different reaction networks. And as you might imagine, such a database requires lots of inputs. So I'm asking for anyone that has published or unpublished rate constant data that they would feel like sharing to get in touch using my email below. And I'd also be looking for people to kind of sign up to have a little look at the database and see what they think about it. So yeah, please do get in contact. And if you forget my email, it'll be on the Planetary Astrochemistry website as well. Okay, so just to summarize, prebiotic reaction networks are really useful tools. However, the fact that they're studied in isolation can cause certain problems. By measuring the kinetics associated with steps along these pathways, we can aim to integrate different networks and try and place constraints on the environments in which this chemistry might be the most productive. In the work that I've presented today, we've measured rate constants for the production of formate via carboxysulfitic chemistry, and we find it to be most productive at a relatively alkaline pH. Based on this, we suggest that Mars sample return should focus on the criteria that we've laid out today of those relatively alkaline pH with UV radiation. And we think that this will be kind of the first step towards getting a more complete picture of this reaction network. And then lastly, please do get in touch if you feel like getting involved with that database. So the final thing to do is to thank everyone who was involved. So in particular, the Leverhulme Centre for Life in the Universe and the Cavendish Laboratory who fund my research. And then also the list of people outlined here have been really helpful for getting this work off the ground. So thank you very much.
Great. Thank you, Skyla, for that presentation. And next, we have another speaker, Lukas Rossmanith, who also is working at the University of Cambridge. And he completed his master's at the University of St. Andrews, where he worked with Ava Stoinkin and Patrick Barth, looking at lightning as a source for fixed nitrogen. And today, or now, his research is focused on how variations in stellar irradiation can impact outcomes of surface prebiotic chemistry. And thank you again for joining us, Lukas. And we're excited to hear from you.
Great. Yeah, I'm going to see if this works. So hopefully, Is this are you able to see this all right?
Right now, yeah, you are in the presenter mode, but it looks, this looks great. That looks good.
Okay, no weird issues
there-
with the slide.
It looks pretty good.
Only
There's a
one weird
small one at the
rectangle,
top.
but it's not blocking anything.
Okay, yeah, that might be my Zoom thing that I can't seem to get rid of. I can get rid of everything else, but I can't seem to get rid of anything, that little thing. So hopefully it won't block anything too important. So yeah, so as mentioned, I am looking more at the side of things with regards to how we can maybe make some conclusions about prebiotic chemistry on exoplanets. And as Paul had mentioned, the best thing about an exoplanet system, or the most visible thing about an exoplanet system, is the host star. So in this talk, I'm going to be concentrating on how starlight, and in particular stellar flux variability in the forms of stellar flares, has an impact on single prebiotic reactions. And so I'm going to start by saying that a large portion of prebiotic reactions, especially when you build from first principles, so very small molecules, and you build up to a more complex system, these reactions are driven by photochemistry. So in the context of a planetary system, you'd have sunlight that would then trigger prebiotic chemistry on the surface of a planet. And so this is sort of like the basic idea. However, not every star is created equal. Some stars are hotter, some stars are colder, and their intensities will also vary respectively, which means that generally speaking, hotter, more intense stars will trigger higher rates of photochemistry on a planet's surface, and therefore will generate more prebiotically relevant molecules than colder stars. And this thinking is the basis of the abiogenesis, so that sort of posits that if we know the intensity of a star, we can sort of basically either we can reasonably conclude whether or not it is strong enough to trigger photochemistry or enough prebiotic chemistry on a planet based on its irradiance. So how does this abiogenesis zone actually come about? Well, this is a basic mechanism that sort of highlights how we can go from very basic molecules, hydrogen cyanide, and SO3, so bisulfate, how we can go from these very basic molecules all the way to RNA pyrimidine via key molecules like glycoaldehyde and glycol nitride, glycol and nitrile. So in order to get there, there are a couple of reactions that we have to be particularly aware of. So first of all, we have to be aware of that there is one reaction that can be triggered without any light at all from these two starting reagents, and that is they react together and they will form aminomethane disulfonate. So this is without any light. With light, instead, we would get aminomethane sulfonate. So this is a very important reaction because if you consider what this reaction unlocks is the eventual pathway down to the RNA nucleotides. If, on the other hand, so if this reaction, this product were to dominate, then we would get over here. However, if the other product dominates, so in the red, we would essentially get a product that does not lead to the RNA pyrimidine nucleotides, and therefore this basically locks out this important chemistry that could be useful for prebiotic reasons. So what Rimmer et al. 2018 sort of defined as the abiogenesis zone is a situation where we have enough stellar light to get 50% yield of the photochemical product as opposed to this dark chemistry product. This also, of course, assumes that this is the only plausible way of making RNA nucleotides, but through this path, but it already serves a very good way to potentially rule out what exoplanets we could consider as being able to drive enough which planets can have enough prebiotic chemistry driven on it by its host star. Using the abiogenesis zone arguments, we can sort of like see which ones are good and which ones fall outwards of that zone. However, this does not mean that all of these planets are necessarily doomed per se when it comes to photochemistry. If we stick with the same chemistry that I've just highlighted just now, there is another way to extend this zone to potentially cover at least some of these exoplanets on this graph, and that is primarily through considering flaring. Now, flaring is a very interesting phenomenon when it comes to stars because it's when a star flares, it rapidly increases its intensity temporarily, and so increases the power that it irradiates onto the surface of a planet. So here from this paper, I just have a graph showing how a typical flare sort of would look like if you were to measure its relative flux, and this flux is relative to the star's quiet behavior. And essentially, by using this argument that flares increase a star's power a lot appreciably more than its quiet emission, it means that you could argue that if a star is active enough, it could have enough of these events where it is able to drive enough photochemistry, and even though it might lie outwit this calculated abiogenesis zone. And so we really want to know, doing these experiments that I'm about to show you, we really want to know essentially if this is a plausible conclusion to make, basically asking the question of, can stellar activity in the form of flaring sort of compensate for essentially for its weakness, that it's able to essentially produce enough chemistry on the planet's surface. And there's a second question that we have to consider, in the sense that when you consider flaring, you're also considering a very irregular, well, maybe not irregular, but you are considering a very varied intensity profile that the chemistry is being subjected to, which means you get time periods where there's a lot of chemistry being driven at the peak of the flare, and very little or no chemistry being driven when the star has quieted down again. So the second question also then becomes, does our method of delivery of photons in this very sort of spiked way actually impact the sort of end results of the chemistry? Does it actually change the progression of the chemistry? And if so, what kind of implications would that have on sort of work that concerns itself with modeling and trying to understand or trying to predict how much prebiotic chemistry we could expect on an exoplanet surface, given a star's flaring activity. So with these two questions in mind, whether flaring is able to drive prebiotic chemistry in the first place and how that might change the chemistry with respect to a system where you're just considering a constant irradiation of the surface, we've sort of have a experimental setup that aims to try and tackle this. So here we have Flare Lab. And like StarLab, we are also using an LDLS, so a laser-driven light source, as a broadband, relatively stable light source that we can irradiate our sample with. In contrast to Flare Lab, our light source, however, in contrast to StarLab, I mean, our light source in Flare Lab is actually a bit weak, quite a bit weaker in intensity. But that is the only sort of major difference between Flare Lab and StarLab, except for also in Flare Lab, we have this moving track, which allows us to move the sample holder backwards and forwards, which will become an important aspect of this experiment. So this is how it looks like, how the light would look like schematically drawn out. It's a diverging light source, which means that when you move your sample, which would be in this cuvette, which would sit in the sample holder, when you move that to close to the light source, you gain more power. The sample would gain more power from the light. But if you move away, then that power drops down. And so by designing by designing motion that can mimic the power profile of a flare, we can essentially simulate experimentally stellar flaring in our lab and try and tackle our questions we have on how that might impact the chemistry. And so this is how a light source actually looks in terms of spectroscopically, contrasted to the AD Leo flare that was measured in 2010. And essentially, what I just want to highlight in this slide is the fact that our light source has a very similar progression to the AD Leo flare. Very sort of when a flare happens, the spectral radiance, as shown here on the y-axis, sort of increases very uniformly throughout the progression of the flare. And as we get closer to the light source, we also see a very uniform increase of received intensity. Not to mention that we're also operating in a very similar, if not the same range as the AD Leo flare when you compare the spectral irradiances. So this light source is quite well tuned to actually simulate, to be our light source for our simulations. So this is how it actually looks like when you move the sample. So in blue, we have a curve that highlights the power that the sample receives over time. So we run two different modes when it comes to these experiments. There is something called the flare run, and there's something called the constant flux. Now, the constant flux is very easy. That's where we do not move the sample at all. It represents by this red line. So it's just uniform power throughout the entire experiment. And then we have our flare run, which is the blue line, as I mentioned before. And this is basically moving our sample first closer to the source, making the power first increase, and then gradually moving it away at different constant velocities to sort of get a rough curve that is analogous to a typical flaring curve. There is also, of course, time between each flaring event where the sample is also immobile. So this is represented in the green dashed line, where, of course, the power doesn't change. So when you integrate this, you can get the energy. And by getting the energy, you get this following graph. And what this graph is basically highlighting is that at the end of the flare event plus the waiting time for the next flare, you have the same amount of energy received regardless of which experimental mode you went with. So this is basically so that we can compare the two runs. We want to give our constant flux samples the same amount of energy in this time frame as the flaring run samples. So that we can see that if there is a discrepancy between the two results, it is due to the way photons got delivered and nothing else. All right, so this is the reaction that we are focusing on. So I've now explained sort of basically the physics and the physical motivation behind this, but we need to now consider a little bit sort of the chemistry side of things. What reaction are we actually going to look at for these experiments? And what we've decided on is focusing on the reaction that forms nitroprusside from ferrocyanide using nitrite as a reagent. And I'll get to reasons why, but in a bit. But already what I wanted to show you on this slide was the fact that one of the main reasons why is that you get a very nice and distinct color change, as you see here. The sample, which starts out as sort of a white, palish yellow as a sample, gets converted to a very impressive red. And you can also see that in solution, where you would start from a very clear cuvette to one that, if you've made a lot of nitroprusside, would be quite a impressive red in your little cuvette. But there are other reasons more than just the color change that would justify this reaction. So when you consider the timescales of different prebiotically relevant reactions, this reaction, the nitroprusside formation reaction, is actually one of the fastest, has one of the fastest timescales. Meaning it is actually quite easy to work with. You get your results quite quickly, and you also get a good color change that you can measure. But also because you can scale things like this, the kinetics and the yield with photochemical reactions depending on the intensity of your light, we can basically use this reaction as a sort of representative reaction to how other similarly photochemical reactions could also behave. So if it turns out that flaring does in fact change the end result of this reaction, then we could reasonably argue that other photochemical reactions that also happen to be prebiotically relevant would also behave in a very similar way, so would also experience a difference if that were to be the case. Conversely, if there is no difference between flaring and just leaving the sample at a constant flux, you could also argue the same for the other reactions as well. So even if nitroprusside tends to not, even if it were to come about that nitroprusside were not so prebiotically relevant, maybe sometime in the future, if anyone really found that out, it still the conclusions from this experiment would be still useful when it comes to talking about reactions that would be confirmed prebiotically relevant reactions. However, I do want to point out that there is also some direct relevance that have been argued by previous papers when it comes to nitroprusside, nitroprusside can go on to make methyl isocyanide, which can then go on to abartically link amino acids, nucleotides, and phospholipids, as highlighted by these papers. So there is also an argument that this is also quite an important reaction, prebiotically speaking, to be investigating. So we here just look at the different absorptive regions of our two main molecules, ferrocyanide and nitroprusside. Here is just a bunch of standards that that we have measured just to confirm where exactly they absorb for our light source. And as we can clearly see, nitroprusside, once the concentration is high enough, does absorb in lower wavelength regions, which ferrocyanide does not, which is very good because it means that this is something that we can use to measure, and we can very easily measure this using a UV-vis spectrometer. And so, once again, this is one of the experimental results that we got for one of our runs. This happens to be a constant flux run. And we can also see as time progresses, in the blue dashed line, you see what we started out with, which is ferrocyanide at 0.1 molar. And then as time progresses, we have this sort of bulging effect. And this is, as previously mentioned, due to the nitroprusside absorbing in lower wavelength regions where ferrocyanide is not active. And so what we can then do is we can then take away the ferrocyanide contribution from this spectrum, and what we are left with is then a differential spectrum, which I've decided, whose values I've decided to call as delta A. And this is just ferrocyanide, the ferrocyanide values being subtracted from my experimental results. And what we see is we see sort of rough peaks at around 500 and 400 nanometers, a bit higher than 400 nanometers to be exact. And this is expected as nitroprusside is most active in these regions. So what we are basically seeing is we are seeing the influence of nitroprusside, or we're seeing the evidence of nitroprusside being formed over the course of this reaction. And then what we can then do is we can take the peak of these spectra, and so the peaks of these absorbances, and we can then basically track that and have scatter plots over time to see how the peaks have grown. And if you run this for 6 hours and you run both a constant flux and flaring runs, what you see is this very very nice result, which has the constant flux experiments basically overlay with the flaring results. This suggests that, at least given these results, that the reaction proceeds in the same way, regardless whether or not you are regardless or not whether or not you're moving the sample and simulating a flare, which means that even though you might expect flaring to only really, trigger a lot of photochemistry in the maximums of the flare, or when it's still relatively high relative to its quiescent position, and so if you would expect that there would only be set periods of time where there'd be a lot of photochemistry, this does still match up with a position where the photochemistry is being generated at a constant rate, because there's a constant rate of photons being delivered to the sample. So this basically means that flaring is, in and of itself, does not change the outcome of a single reaction, such as the one forming nitroprusside. But it also suggests, on the other hand, that flaring can drive photochemistry. So it's not the case that it's not able to build up enough product so that you can measure it. It is still possible. You can see product and good amount of absorbances at the end of the experiment using flaring. So just to summarize, whilst photon delivery may not matter, flaring can produce nitroprusside, which would suggest that planets such as M dwarfs, which are quieter and therefore may be initially excluded from the abiogenesis zone, may in fact be included if their activity is high enough to compensate for their general coldness, meaning that if you just use their quiescent flux, they wouldn't be able to drive enough photochemistry. And this result would also then validate a recent approach in 2020 when it also looked at that based on how much stars flared depending on their type. So into 2020, looked at using test data, looked at how M dwarfs found that M dwarfs would flare a lot. So this would be quite conceivable that a very active M dwarf could compensate and be in the abiogenesis zone. But the key thing to remember is that basically only the energy in the end actually really matters, and not how you deliver the photons to the surface. However, this does not mean that a wider network couldn't be impacted by flaring. The outcomes of a more complex scenario where you have different sinks and sources interplaying with each other, as Skyla was giving a great talk about just a moment ago, the outcomes of that could still be affected through stellar variability and through flaring. And yeah, so these are still only sort of quite, these results look nice, but they are still rather initial results, as we plan to change more parameters and do more experimentations with these flares to really solidify the conclusions that I've presented to you today. And just very quickly, I would like to thank everyone, and I would also like to thank, of course, Paul and for being a great supervisor, and I would also like to thank Sam and Sophia. They are so Dr. Samantha Thompson and Sophia K. Platimesi. They worked a lot on actually also building Flare Lab so that I could use it. So that was so I'd also like to extend acknowledgements to them. But yeah, that was my talk.
Great. Thank you for that presentation, Lucas. And also thank you to Paul and Skyla for your presentations. And now we still have some time for some discussions. So if anyone has any questions or comments for any of our speakers, they're welcome to type their questions into the chat, or you can also use this raise hand feature in Zoom, and then you can go ahead and ask your questions over your microphone if that's something else you'd prefer to do. So yeah, we do have time for any of those questions from anyone in the audience. So I had a question, I think, for Skyla. And you mentioned Mars sample return. And do you know if any of the samples that have currently been collected already would be something that's kind of ideal to test some of your experiments and models?
Yeah, a really good question. So I put up a picture of Wildcat Ridge in Jezero Crater, which is quite like a sedimentary area where we think those lakes might have existed. So potentially something like that. But I think there are probably better candidates. So yeah, we'll just wait and see what the Mars sample return mission continues to produce.
Right. Yeah, that'd be really exciting to see what comes back and to compare with some of the things you guys have been working on.
Yeah, for sure.
I do see, I think Donald Burke has his hands raised. So I'll ask you to go ahead if you're there.
Yes, working on trying to activate the camera there, but that's my audio is enough. I'm intrigued by this observation that the flaring was not having a different outcome than the constant irradiation, and so the total photon flux integrated over time ended up being about the only major contributor. That seems like, I mean, as one who does not think about these questions, I would naively think that perhaps what's going on there is you have a single step in your reaction that is light sensitive. And once it absorbs a photon, there's no other additional light sensitive things downstream of that. Or that the initial photochemistry generates its product directly rather than accumulating a reactive intermediate that can dissipate before it can move on. In other words, a spike in the irradiation, I would think, could produce a lot of something that might need to accumulate to a high level in some reactions, maybe not in yours, but in some reactions might accumulate to a high level, and that high level would then be needed to go on to subsequent things. And that the outcomes that you're looking at here might be generalizable to some subset of reactions, but other reactions might behave very differently. So sorry for the disjointed question, but can you glean anything useful from that and say it in a more coherent way than I did?
Yeah, I can certainly try. Yeah, so I mean, to your first point, so I didn't really go in detail with the mechanism of actually what's going on and what is being photoactivated in this reaction. But the way I understand it is that I think you're right in the sense that when it comes to the ferrocyanide being photoactivated, this is mainly this initial step that is the light sensitive step. And as far as I understand the reaction, it seems that the subsequent steps would lead to nitroprusside would not require light. And so this could explain why it still overlaps, because you still get, as you said, enough being generated so that it all goes to the same point. I would say that I think it is an interesting point to consider how many photochemical steps are needed in a mechanism. It might well turn out that we would need to be a bit more careful with generalizing our conclusions. And it might be the case that if there are multiple photo light steps, that it might lead to a different outcome. But to that, I also would like to add that eventually, if you try and broaden out to too many steps, you might end up then looking at more of a wider chemical network, which will involve multiple photon steps. And in that case, definitely you can't just use these results to say that everything will be the same. In that case, it would be quite plausible that flaring, when you look at the wider network, actually could have a outcome. So I guess the sort of point is how narrow is your scope going to be? If you're only really looking at a very narrow set of steps, then I think these results, should nothing else come about that may directly contradict them, could actually end up being generalized to other photochemistry.
Brilliant. Thank you on that.
Great, thanks. So there are some questions also in the chat, and there's one for Skyla, and it's from AC. They're asking if pH 9 conditions appear to be optimal for the reaction conditions, what environments would produce such alkaline conditions if aqueous pH in a CO2-rich atmosphere would produce lower pH conditions?
Yeah, so good question. We can envision these kind of pH 9 style conditions in quite a few different ways, but the most promising thing that we focus on are carbonate lakes, so soda lakes. And these end up forming when you have water in sort of a closed system like a lake, and you end up dissolving quite a large amount of carbonate minerals. So things like the calcium carbonates, which is why we're quite interested in finding those on Mars. And so you end up getting quite high concentrations of carbonate ions. Those can then end up leading to an increase in the pH of the water. And then that would result in these pHs of around 9 to 12. So we're obviously looking at the more 9 range of that based on what we've found. In terms of in a CO2 rich atmosphere, I guess we're kind of assuming in the system we're thinking about that these would be obviously not too rich in CO2 that you'd end up messing up with the carbonate equilibrium that you would have going on. But yeah, obviously changing those kind of atmospheric parameters to look at the partial pressures of different species like CO2 in the atmosphere would be interesting to see how these networks actually respond to that on a wider basis as well. I hope that answers your question somewhat.
Great, thanks. And there are some more questions from people in the chat. One is from Srija, and I think they're asking Lukas, how do simulated stellar flares, such as those studied in the AD Leo system, influence the formation and evolution of prebiotic molecules on planets exposed to such radiation? I'm sorry, I think, is everyone else able to hear Lukas?
Is it working now?
Now, yeah, now it's working.
Oh, okay. Sorry. It seems that Zoom for some reason cut off my audio for a second. But yeah, so essentially this is sort of from the view that photochemistry is an important part of building a large stock of prebiotic molecules that can then, the idea is then react together to form things like, eventually you'd lead to things like RNA and DNA and phospholipids and so on. So you then sort of build a more complex system. And I guess, the question that I was asking myself when it comes to conducting these experiments is, can we get enough photochemistry generated with flaring? And if there is a difference compared to sort of a constant flux where we're not considering flaring, but we're considering maybe a more a comparable quiescent stellar irradiation situation. So if we can answer that, if there is enough prebiotic chemistry being generated through these photochemical reactions, and if we can say that that's the case, if flaring is able to let us do that, it means that it allows those stars who may, if they were quiet, not generate enough photochemistry. It would allow them to generate enough photochemistry. And I guess you could then take the long view that if you have enough photochemistry being generated, that would then lead, if the conditions are right, to things like evolution of those molecules and microbial life. So it's more of a case of, is the chemistry possible, and to what extent might that differ from a non-flaring scenario, as opposed to as opposed to just as opposed to trying to saying how exactly it changes, I guess. I don't know if I've answered the question, but does that make sense?
Yeah, thanks for going into a little more depth for all of us. And we do have a little bit more time, and there are more questions. So there is one from Roberto for Skyla asking if you have started to, or if you have any plans to incorporate reactions involving phosphates into the networks you're working on.
Yeah, so obviously phosphate is super important in biology. So getting towards a system where the phosphate doesn't end up hindering some of the reactions we're working with would be good. At the moment, we do actually have some phosphate in our system because phosphate acts as a very good buffer. And so when I'm trying to keep the pHs stabilized at either 12 or 6, we've got a phosphate buffer in there. So we can see that it's not significantly impacting our chemistry in a negative way. And then, yeah, in terms of exploring new reaction networks that involve phosphate, that's definitely something that is on the horizon. And it would be interesting to get some rate constants for those types of reactions as well.
Great. I think we do have a bit more time for maybe one or two more questions. I see that Kevin Devine has his hand raised, so if you'd like to go ahead and ask your question, Kevin.
Okay, thank you, Skyla and Lukas, for two fascinating talks. I really enjoyed them. Looking at where you're coming from, I presume you're thinking of the importance of sunlight and UV light in particular to drive prebiotic chemical reactions, which eventually lead to the production of important biomolecules such as amino acids, phospholipids, and nucleotides and sugars. If you think outside the box, you think about dark but potentially energy-rich environments, such as the icy moons like Europa and Enceladus, and possibly Titan, something weird like on Titan. How would you go about trying to sort of see what's forming there? I would have to think, well, on Titan, you could still use UV. UV is still important, but on the other two, presumably other radiation sources would have to be taken into account there to try and study what prebiotic molecules could form under Europan or Enceladian conditions.
Yeah, I mean, I think, you're right, there's more than one source of energy when it comes to these reactions. And I mean, I don't know what exactly is under the ice sheets of Enceladus or Europa, but if there is anything interesting, then it might be I don't know, we here on Earth we could imagine there might be there are hydrothermal vents, so maybe there are some on Europa, but I guess but to be honest, I'm not entirely I don't know how you would go about observing this except except if you actually went there and maybe drilled through the ice sheets
Yeah,
of
I mean, creating a
Enceladus.
model for it. How do you actually simulate Europan and Enceladian conditions on Earth? What sort of reaction vessel would you set up? I mean, I presume Europa is exposed to the sort of radiation belts of Jupiter, so I presume there's particulate radiation going through. There may well be a rocky core with some volcanic activity, as there certainly seems to be on Enceladus. So, but as you said, this is the big question of where did life start? Did it start in more than one place? I mean, or what I tend to think of, I agree with what Paul said, the shallow hydrothermal surface vents. I think that's most likely, but I think you require the essential molecules come from different places and need to be sort of circulated around the planet involved. So, like for example, Earth and Mars, I'm pretty sure it's the importance of solar radiation is what drove the evolution of life here. But elsewhere,
Yes.
Yeah, if just real quick, I threw a couple papers into the chat. One with Zach Adam and Albert Fehrenbach and a couple others about radiolysis and some radiolysis experiments that have been looked into. Radiolysis is something you'd expect subsurface. There's also some really interesting work looking at the detection of HCN in diverse redox chemistry in a plume of Enceladus. And I think a lot of people are interested in subsequent electron beam experiments. And there's electron and proton beam experiments that are being run by Kobayashi's group at ELSI. I think that there are a few different groups that are looking into this, and some of them have found some promising ways to form amino acids, sugars, various other things at a variety of yields.
Thank you, Paul. That's very. I'll make a note of those.
Yeah, just to hop in quickly, I guess when we're thinking about creating these kind of models, obviously our group is very focused based on our resources on using UV radiation to produce good productive chemistry. But these kind of models can take into account networks that we might expect to happen on sort of subsurface environments or within hydrothermal vents that are deep sea vents and things like that. So obviously incorporating those networks will be really, really important to get a really good overview of the different environments that could have contributed as well. So that's something, you know, that we would be thinking about in the future.
Right.
And I guess just to add also, you know, when it comes to maybe arguing about habitability on other exoplanets and maybe the emergence of life in the wider universe, whilst I would agree that looking at a wide variety of sources is important, you know, the most observable thing we have with an exoplanet system is a star. So I think, you know, the more we know about exactly how starlight in particular affects the wider chemical system of a planet, the more we can glean conclusions about what might be possible on those exoplanets, and maybe come to a conclusion whether or not they are able to, in the long run, make some life or not. But of course, they might not be complete conclusions if we're just considering the starlight. But I guess it's the view of we're also concentrating on a single light source, a single energy source, trying to understand its effects as best as we can.
Great. And I think we've gone a little bit past 1:30. So I think maybe in the interest of keeping to the schedule, we might go ahead and end here. And so with that, I think we would all want to thank Lukas, Paul, and Skyla for their great presentations. And thank you all for joining. So we hope to see you again at the next session.
Thanks, everyone.
Thank you.
Thanks.